All right, so we talked about open addressing just now. We actually implemented fairly quickly the insert, at least a basic insert, and that one looks pretty good overall. We have a subscript which works for all our test cases, although I've mentioned that it's not completely correct, but we're going to get to that momentarily. But before we talk about that, I want to jump back up to here with insert, because what happens if we go here, let's create test case 4, and this is still part of get, which is fine. We'll create 100 of them, and then we'll do for int I equals 0, I is less than 1, 20, I plus plus. We'll do I plus 42. Actually, let's see, are we allowed to, does C++ allow you to concatenate things? Let's see. Let's see what happens when we run that. Whew, infinite loop. Well, what's happening, and hopefully this is somewhat apparent, is that we're stuck in here trying to find an item that's not used, right? Okay, one thing we can do is just double or increase the size once too many items are used. That's one way to do it. I'm going to skip a bit because the problem with open addressing is that if it gets full, it takes a long time to do search because you're searching through a lot of items. So what they do instead is what's called a load factor. And the idea here is that for open addressing, if the load factor, which is the percent full, so 0.5 means 50% full. If it's less than 50% full, you're wasting space, aka you have too many extra items, and they're not helping you. In general, if it's greater than 80%, you have significant overflows. In other words, you have a high number of collisions, and you're having to do a lot of probing when it's above 80%. So your load factor is what your current percent full is. The idea being that once you go beyond these bounds, you want to readjust your array to make it more efficient. Now for open addressing, it's between 50% and 80%. For chaining, it's between 100% and 200%. That makes sense in chaining because you are allowed to put multiple items in the same location, so that's okay. Open addressing can't be over 1 or 100%, obviously. Okay, so that's what the load factor is, number of items in the hash table divided by the size. And let's jump over before we talk about deleting. Let's actually jump to the lab. So when we're talking about the load factor, implement a hash table control checks the integer and a load factor, insert, remove. All right. So I didn't tell exactly here, but insert, remove, which should be in here.
Percent full.
Percent full returns your current load factor, or the percent full it is. The load factor here specifies at what point you need to increase the array. In this lab, we're only going to worry about the upper bound, not the lower bound. So if you're below 50%, don't worry about it. But the upper bound is going to be sent to you as a load factor. It's not a set 80%. I'm going to pass it to you. You can see that in the example here, where I'm passing in 0.8, aka 80% full. Okay, so the first thing we want to do is we actually want to calculate what percent full is. So
just had the slide open. The slide against the thing.
Okay, I'll give you the slide. I think. Here it is.
Load factor, number of items.
In hash table divided by array size. Oh, how many items are in the array?
Yeah, I was just like,
oh no!
We don't have pushback, so the size isn't how many items we have.
No. What do you think we need to do?
Part of me is make a counter.
Yeah, let's make a counter. None? Sounds great. We can't quite do that. Can we? I only ask myself because C++ sometimes starts adding things. Wow. It took it. I wonder what that means. All right, so C++ has changed it to where I guess you can do that. That's actually kind of cool. Alrighty then. Well, we need to make sure we...
Yeah, it added things. So.
Well, yeah, let me let y'all do that. All right, so now we have num. Excellent. Let's go finish out %full. So let's also see if I have a test case for that.
Oh, wait, those are both integers.
Oh yeah, yep. So I have 100% full, should be 0, then you add 1, needs to be between. So when you're testing a floating point, you have to have a delta to say it needs to be within this range. Otherwise, it's going to not be correct. Because trying to test equality on a float is a very dangerous thing to do. Don't ever do that. It'll end poorly. We will go in more detail about that in architecture. Just note, don't do it for now. So that's why there's a delta. We want 0.01 within a range of accuracy of 0.001 because it's floating point. So it can be, what this means is that this can go from 009 up to 011. As long as it's within that range, it'll pass this test case. No, that's a little weird, but that's all right. And if we run it, I think you already mentioned what the problem is. We kept getting, what we kept getting, 0? Expected 0.1, found 0. So it kept returning 0. Why is it returning 0?
Floats.
Yep, we need to convert these things to floats.
Just cast one of them as a float.
I usually like to cast the denominator as a float, but either should suffice. Or the new, yeah. You can also just cast them both because that's what has to happen. They both have to be a float. You can't. The computer doesn't do float integers. It does a conversion first. All right, let's see what that does. All right. Okay. What's that?
In procedural programming, we had to use static cast.
Sure. If you really want to, go ahead. That's all I got. All right, so let's do another test. I don't know, less than 70. So what should the %full be at this point? 0.7, right? Because we've added 70 of 100. Whoops. Let me actually add something. I didn't like that. It's because these functions have to have a different name. Okay, great. Now, so that's 70%, and it's an 80% load factor, so if we add 30 more, what should the %full be afterwards? All right, this might be a little tricky. What should this be? So is that 70? 70 out of 100 is still less than 80%, so obviously it fits in there. Let's see, but we're going to cross the threshold here, and we're going to have 100 items, which is definitely past the 80%. So the new question is, what value should it be? When you hit the load factor, you should double the size of the array. So, when you're at 100, what should the size of this array be? 200. And if there's 100 items in it, then the load factor should be 0.5. Yep. Did everyone follow on that? Excellent. All right, and then we failed. Oh, it didn't get the 70% either. Really? I just run it again.
Maybe it's because delta wasn't used.
Did I not? Oh, did I not put a delta in there? Oh, I didn't put the delta. Yeah, you have to have that delta, or it's going to fail. All right, way better. Okay. Found 1 and not 0.5. Why is that? Well, we're not actually increasing the size. So, we need to increase it during insert. Oh boy. Well, first we need to detect if it needs to happen. So let's go do that first. A lot of times if you don't know what to do, figure out what needs to be done to set it up is a good way to start. We already have percent full, right? So percent full will tell you. Oh, yeah. I think I see what you're saying. They're percent full. And if percent full is greater than well, we want it to be if it's greater than this thing, right?
But could we actually call the load factor into insert?
Right. So we pass the load factor during the constructor. Do we store it? No. Okay, let's go fix that. One moment. You called a load factor there. All right, I'll do that here as well. All right, so I typed some code. Where are we? Did I go past it? Oh, here we go. Type some code. It's usually good practice to go ahead and run your test again just to make sure you didn't mess something up. Trust me, just do that, please. You'll save yourself a lot of time. We didn't mess ourselves up. That's great. All right, so if the percent full is greater than the load factor, what do we need to do? Here's a good question. Is it a lot of work or a small amount of work?
A lot of work.
Let's call a function. What do we want this function to do?
Make a new one? Is that one? Has this been
I mean, no, you're right. You're right. Make a new one.
Wow.
Yeah, we want to go ahead.
Double the size.
All right, let's call it that. Just literally call it whatever function you want to call it. Double. Perfect. Semicolon. This is a really good way to go about it, because when you're going in an interview and they're asking you to implement something, just say, I'm going to pretend like this function exists. I'm not kidding. I'm not joking, because you say, I'm going to pretend this function exists. I'm going to write the rest of this code. The rest of this code's good. Now I just need to implement this function. It's a really good way to do it, especially during an interview, because then you can piece it off and then go and jump back to it later. And a lot of times in interviews, they're going to be like, you don't need to write that function. I got it. And then you don't even have to do that. It's amazing. But anyways.
All the hard things.
What's that?
Do that for all the hard things.
Right. Yeah. Because a lot of times they're focused. They want to make sure you understand this part. They don't maybe care that you know how to double the size. You probably figure that out later. The thing is, during an interview, they're looking for certain pieces, and also during programming, this is a good way to do, because notice that we've tested everything else. Now we just need to test this double size thing. It's a very good way to do it. It is called divide and conquer. It's technically what this is called, but I'm trying to emphasize that, hey, look, you can also use it to keep your functions small and easier to read as well. I don't know if there's any other way I can tell you, please just do this. It'll make your lives better. I had one guy I worked with who thought everything should exist in main and you should never make a function call and you should only use gotos. He did not last long. All right, but we do need to actually declare that function, so let's do void, what's called double size. All right, we need to double the size. Oh, man. What's that?
We gotta make a new hash table.
We got to make a new hash table. Well, we don't have a size variable, so make that local int, or size t, or whatever you want to call it.
Oh.
We don't have a size variable. I think what I actually think you meant was this.
Yeah.
All right, cool. Actually, could you do this in place? I've never thought of that. Could you just iterate through the table, and if it's in use, hash it? Ooh. No, I don't need to do that. No, you can't do that.
Explains why you never thought of it before. You
Yep.
probably just forgot.
I was like, is that even possible? All right, let's create a new hash table. Well, that's interesting. Make a whole new table altogether. Huh. Let me think what was trying to be said was this. Is this the new Ketchum? There we go. Ooh. What's new Ketchum size?
Size.
All right, let's go do that. Let's resize it. All right, so we resized it. Now we need to put all the old elements in it, right? I mean, yes, we need to put all the old elements in it. So let's iterate through. Well, there's a hard way to do this and an easy way to do it.
Oh, let's find the easy way.
All right, hang on. Whoa, 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 no. Oh, I'm sorry. Someone was doing it. Go ahead. Yes, catchem.size. Right, okay. All right, so let's do it this way. Let's instead make a vector new catchem, or I'm going to actually call it the old catchem. And that'll be of catchem. So that's going to copy everything over. Ooh, that's going to be a costly operation, but you know, whatever.
This one's not graded.
This one's whatever. And then I'm going to go, after that, I'm going to go through all of catchem. And we're going to do catchem dot sub I dot used equals false, right? Invalidate them all. And then we're going to go ahead and resize catchem, which is our array. And then we're going to now go through old catchem. And why did I go through all this work? Yes, do it. Yeah, old catchem, because the old catchem is currently contains all the values. All right. Only one problem. Do we want to add all of them? Oh yeah, so we need to put an if in front of it, yep. Okay. All right.
Catchem is used.
Yeah, old catchem.used. And this may give us an error on this thing up here. Let's see what happens. It didn't. Interesting. Okay. But this time it found 0.6524. All right. It might be hard to see the problem.
I think between this and the last one, I was beginning to notice a pattern.
So keep in mind that when we call insert, we increase num. Yeah. Do we need to set num to 0 first?
Yes.
Yeah. Yeah, the doubling is not fun in this one. There! All right. Whew. Well, that function was a little, yeah. There were a lot of gotchas in that function. This is not exactly the fastest way, because of course we're creating a new vector of the old items. A faster way to go about this is to actually store a pointer to the vector and then use pointers. Do we have time for that?
Let's not, please.
But you see why the pointer would be faster?
Yes.
Because, yeah, okay. Because here, you just, yeah, you just allocate a pointer to the new vector, resize it, and then copy it directly over. You don't have to do this initial copy. Yeah. All right. We'll just live with that. So So then the load factor became better. Oh, and will that get rid of our infinite problem with get? Yes, it did. Kind of, sort of. We got some infinities.
Honestly, that looks like HTML to me. That looks like my HTML output.
Well, that's interesting what happened there. Let's see if we can fix that real quick. Is it? It might just be test 4. Is it test 4? Because let's move this to 20. Let's see if that passes. Yeah, so that one passes. 40. Oh, there ain't. Oh, that's weird. I'm kind of curious what's going on with that. Wait, hold on. We plus 20, and then when we print it off, why is it doing that?
String plus an int.
Oh, that's, never mind. Ignore that. That's wrong. That's what we want. Because it's a, yes, that was my fault. Sorry, guys. Because obviously if I'm doing a character array and I'm adding an I, that moves the character pointer over, because it's actually a pointer to the A, and then you're adding I to move it. Yeah. My bad. That was me. Sorry. Sorry. That was me. That was all me. That was all me.
It's your fault.
Totally my fault. Yeah, yeah, yeah.
The last hour we've been under the lie of prefixes.
I don't know. 102 should be blank. I don't think that's the case. I mean, should fail. Yeah, you should find an answer. On the flip side, 0 should be blank. Yeah, 0 should be blank. There we go. And we don't overload, which is what we were trying to work on. Perfect. Okay. Any questions about the load factor? I'm going to, real quickly, I'm going to skip deletion real quick. I'm going to get back to it, trust me.
Yeah.
So this is the important part to keep in mind before we do delete, because that's going to get pretty hectic. So what these graphs are comparing are the first two, the black and the red, are a open addressing, so you have linear probing and double hashing, and the green is separate chaining. And down here is what the load factor is. Now remember, the optimal load factor, for the green, is between 1 and 2. So I don't know why they even show the green on these pictures, because it's it makes it look like it's the best, but that's not what's going on. But what they wanted to show you is that linear probing is basically the worst. And what's going on is this is the number of probes. So the higher is worse, aka it takes longer to get to the selection. Notice that there's a big gap between linear probing and double hashing for unsuccessful search. So you look for it, you can't find it. That makes sense, because as it gets full, you have to go and probe more in order to find it. Let's see. Oh, that's the only picture we get? Oh, here's successful search. So successful search, meaning you do find it. Notice that the double hashing is really good. You only do pragmatically up to 5, we'll just say, at most. So your O of 1 is basically 5 searches, while your load factor for linear can get really high if, again, this 0.8 is really where it starts to jump out.
And that's why we use 0.5 to 0.8.
Right, that's why we usually 0.5 to 0.8. I think, do I talk about Java? I thought Java, well anyways. When should you be concerned about open addressing and separate chaining? Generally not, because you're going to be using a library most of the time anyways, but you want to keep that in mind, because if you know the number of items to be inserted into the table, open addressing is actually going to be pretty handy, because you just, as long as you are okay with that 20% buffer, it's going to be a lot better for memory than having to store all these pointers. Hopefully, unless of course what you're storing is a lot of data. Then maybe not. But then again, you can make your hash table of pointers and then get around that problem as well. Yeah, do you know what the expected load factor is going to be? Does it just go up to a certain point and then you just search it from there, or are you going to be adding and removing? Hash tables, the default load factor in Java is 0.75, so that's 75%. This function or data structure was so important, or actually is so important to Java, that from version 1, every object has to have a hash code so that every object can be intrinsically hashed or used in a hash table. It's hard to, I guess, fully explain to you how important this data structure is, because it's usually the go-to data structure for most people. Just use a hash table if you don't know what to do. Because most of the time you're not going to iterate through it. You're really just inserting it, deleting, and searching, and its average is O of 1, which, how can you do better than that? So a lot of times hash tables, if they make sense, because remember it's a key value, not just a list, hash tables are usually a pretty big go-to. Okay. But the load factor is very important for open addressing. All right. Now any questions before we do delete? No. All right.